Welcome to this lecture series in group theory. In this lecture, we'll illustrate the use of the orbit stabilizer theorem by means of a number theoretic application. I think it's a very nice application of the OST, although one can prove that using elementary number theory. So we'll get there, but let me first recall the main things. So suppose we have a group G acting on a set X, and if X is an element in the victim set, and this denotes the orbit of X, which means what? Which means this set. You hit X by all the elements of G, and whatever you get, you collect in a set and call it the orbit of X. And you have another notion, which is the stabilizer of X, which is those group elements which fix X. So those are two natural notions. And the orbit stabilizer theorem says that the cardinality of this orbit is equal to the index of the stabilizer of X. So the subscript is there to emphasize which group that we are talking about. Usually there is only one group that we are talking about, so there is no confusion and one may drop it. But I, as a force of habit, put it. All right. So here is the example that we want to prove. This is a purely number theoretic statement. So if p is a prime and you have some integer k in this range, so it is strictly less than p and it is at least 1, then this number, this binomial coefficient, is divisible by p. I encourage you to try to prove this using elementary number theory before we look at this proof using group theory. So here is the proof. So let X be the set of all subsets of Z mod Pz whose size is K. So X is the collection of all subsets of Z mod Pz which have size K. All right, one can also denote this using this nice notation, which is Z mod Pz choose K, but yeah, this is perhaps not so familiar generally. Okay, so that's X, and the group is Z mod Pz, and we define an action of G on X as G dot X, G dot S, let me write, G dot S, S is an element of capital X, this is equal to G plus little s in S. Right, just translate everything in capital S by the group element. This addition is happening in Z mod Pz. Both little s and little g are elements of Z mod Pz, so it's legitimate to take this sum. And yeah, so that's G dot S. One may also write this as G plus S. That's a better notation, but let's just stick to it maybe. Okay. Yeah, so let me write this also as G plus S. Maybe I will slip and use this. Both are just notationally. The difference is purely notational. Okay, so this is an action. Check that this is an action. Just check the axioms, very simple. And here is the point. So let S be some arbitrary element of X. We claim that. We will show that. So yeah, I don't have a good color. We will show that orbit of S has size 1. Sorry, what am I writing? Stabilizer of S has size 1. So basically the stabilizer is the trivial group. The only element in it is the identity of the group G, which is the element 0 bar, or we may just write it as 0. So this is the first thing that we want to prove. And the proof is very simple. So let G be in the stabilizer of S and say G is different from 0. So when I say 0, I really mean 0 bar, which is all the integers divisible by p. That set is an element of Z mod Pz and is the additive identity of that group, the identity of that group. So pick a non-identity element and suppose it is in the stabilizer, then we want to say something goes wrong. We want to bring to a contradiction. So then first note that this, the subgroup generated by G is everything. because in this group Z mod PZ, every non-identity element is a generator, right? So the generator is everything, and hence, and thus there is n some natural number such that n dot g equals 1. What is n dot g? N dot g is a shorthand for g plus dot 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 g, this n times. So this is n times, just a shorthand, right? Immediate by this equation, we have the existence of such an n, and therefore, thus 1 belongs to stabilizer of S. Clearly, because stabilizer is after all a subgroup, so it is closed under addition. If G is in the stabilizer, then all these things are also in the stabilizer, and therefore 1 is in the stabilizer. Again, by 1 I mean 1 bar, which is all the integers which leave a remainder of 1 when divided by p. So please be mindful of that. Okay, now finally, since 1 is in the stabilizer, we have therefore 1 dot s is equal to s, which implies 1 dot s equals 1 dot s, which is equal to s. What did we do? We had 1 dot s equals s. We just hit by 1 on both sides. So of course we get this, but 1 dot s is s by the previous equation, so we have that. But by properties of the group action, 1 dot s is 1 plus 1 dot s, right? This just clubs into the group operation between 1 and 1, and that is just the addition. So basically, if you just keep doing it, you will get that k dot, let me not use k, maybe a dot s equals s for all group elements. So the upshot is that as soon as you have some non-identity element in this stabilizer of S, it turns out that everything is in this stabilizer of S. And if everything stabilizes S, basically it just means that S is the entire. This implies that S is equal to Z mod PZ. Right? So I mean, you can obviously figure this out by yourself, but suppose S was just 1, 2. Suppose K were equal to 2 and S was this set. And just by saying that 1 stabilizes it, and let's say the prime is 7, and saying that 1 stabilizes this thing, which it just means that 1 plus 1 and 2 plus 1 is the same set as the above one, but that's not the case. So that gives you a contradiction. Basically, if 1 stabilizes some subset, that subset has to have everything. As soon as that subset has one element from the group, it has all the elements from the group. So another way to say it, suppose A is in S, and since 1 stabilizes S, 1 plus A is also in S, 2 plus A is also in S, and so on. So all of the group elements will turn out to be in S. So that is another way to say it. So that's the conclusion. S is equal to Z mod PZ, but then the size of S is greater than K, because K is strictly smaller than P, and here we see that the size of S is P, but S had size equal to K, and we have a contradiction. So basically, all in all, we have proven this statement. So that claim is proved, and now by the orbit stabilizer theorem. So by orbit stabilizer theorem, the size of the orbit of S is equal to the size of G, the index of the stabilizer, but the stabilizer is trivial, so it is just the size of G, which is P, right? So the orbit of any element has size P. That's what we have shown. But at the same time, X is partitioned by orbits, and hence P divides the size of X, and that's what we wanted to do, right? Every orbit has size P, and X is partitioned by orbits, and hence X is partitioned by things of size P, and hence P divides the size of X. So yeah, that's the end of the proof. This is longer than your elementary number theory proof, but you can visualize it. So I encourage you to see what's going on in this proof. Find out all the orbits in some small example. So take, let's say, the prime as 7, K as maybe 3, and see what are the orbits. Just draw them on paper. And yeah. So that is an example to illustrate the orbit stabilizer theorem. And I'll see you next time.